The enigma of information and black holes when matter, energy, or data crosses the threshold of a black hole. We confront a paradox at the heart of modern physics. Imagine a single particle, defined by its position, velocity, and other intrinsic properties, plunging past the event horizon, the invisible boundary from which not even light can escape. At that moment, the information carried by the particle appears to vanish from the observable universe. This raises a troubling dilemma. Quantum mechanics insists that information is never truly lost, while general relativity suggests otherwise. This tension has given rise to one of physics' most puzzling debates, the black hole information paradox. Stephen Hawking once theorized that information could be lost forever inside a black hole. However, this idea runs counter to the principle of quantum determinism, which asserts that the future and past of any system must be derivable from its present state. More recent developments in string theory and the concept known as the holographic principle suggest a possible resolution. Information might not be destroyed, but instead encoded on the event horizon itself, much like a cosmic hologram. Another intriguing possibility is that Hawking radiation, the theoretical emission from black holes, could allow information to slowly leak back into the universe, though in a form so distorted it remains incomprehensible. Reconciling these ideas is key to bridging the gap between gravity and quantum mechanics, a challenge that continues to inspire physicists around the world. The birth of cosmic giants, supermassive black holes lurking at the centers of most galaxies are supermassive black holes, behemoths with masses ranging from millions to billions of times that of our Sun. But how did these giants come into existence? One leading theory suggests that they began as smaller intermediate-mass black holes, which grew over eons by devouring gas, dust, stars, and other matter. Through relentless accretion and mergers with other black holes, they expanded to their colossal sizes. Picture a cosmic predator endlessly feeding on everything drawn into its gravitational domain. Another hypothesis proposes that supermassive black holes formed much earlier than previously thought, just a few 100 million years after the Big Bang. In the early universe, immense clouds of gas may have collapsed directly into black holes, bypassing the smaller stellar phase. This direct collapse model might explain how such massive entities could exist so soon after the dawn of time. Galaxy collisions also contribute to this cosmic evolution. When galaxies merge, their central black holes often spiral toward each other and eventually coalesce, producing an even more massive object. The surrounding turbulence funnels fresh material toward the galactic core, accelerating the growth of the black hole. Over billions of years, these titans shape the very structure of galaxies, influencing star formation and galactic dynamics. Understanding their origins sheds light not only on black holes themselves, but on the evolution of the universe as a whole. Hawking radiation. When black holes evaporate in the 1970s, Stephen Hawking introduced a revolutionary idea. Black holes aren't entirely black. According to quantum theory, empty space is never truly empty. Instead, it seethes with virtual particle-antiparticle pairs that pop in and out of existence. Near a black hole's event horizon, these pairs occasionally materialize such that one particle falls in while the other escapes. The escaping particle appears as Hawking radiation, effectively carrying energy away from the black hole and causing it to lose mass. This process, though unimaginably slow for large black holes, leads to the gradual evaporation of the black hole over time. For stellar or supermassive black holes, this might take longer than the current age of the universe. But for tiny, hypothetical black holes, the loss of mass could accelerate dramatically, ending in a final, explosive burst of energy. Hawking radiation not only offers a potential explanation for black hole evaporation, but also provides a tantalizing bridge between quantum mechanics and general relativity. suggesting a deeper unity between the physics of the very small and the very large. Tapping the power of rotating black holes, could black holes be harnessed as an energy source? Surprisingly, the concept is more science than fiction. Rotating black holes, known as Kerr black holes, possess vast stores of angular momentum and gravitational energy. In 1969, physicist Roger Penrose proposed a method, now called the Penrose process, to extract energy from these spinning monsters. The process involves sending a particle into the ergosphere, a distorted region of spacetime outside the event horizon where everything is dragged along by the black hole's rotation. Under the right conditions, a particle can split in two. One part plunges into the black hole, while the other escapes with more energy than the original had. This surplus energy is effectively stolen from the black hole's rotation. Although purely theoretical today, such ideas stretch the imagination and hint at what future civilizations might one day attempt. Peering into the cosmic unknown for countless generations, humankind has turned its eyes skyward, hoping to unravel the secrets of existence. But with every answer the universe yields, even more profound questions arise. From the mind-warping physics of black holes to the tantalizing possibility of ancient extraterrestrial visitors, the cosmos presents us with puzzles that defy logic and stretch the limits of our understanding. Join us as we embark on a journey to uncover the most bewildering mysteries of the universe. The vanishing of information, a black hole paradox. Whenever matter, energy, or even data is drawn into a black hole, we confront a conundrum that lies at the heart of modern physics. Picture a single particle, its characteristics, like speed and position, meticulously defined. As it crosses the event horizon, the invisible point of no return, its information seems to disappear entirely from our universe. This apparent loss stands in stark opposition to the principles of quantum mechanics, which assert that information cannot simply vanish. The contradiction between this quantum rule and the predictions of Einstein's general relativity gives rise to one of physics' most perplexing challenges: the information paradox. Stephen Hawking once hypothesized that information swallowed by black holes might be lost forever. But this idea directly conflicts with quantum determinism, which insists that a system's future and past must always be deducible from its current state. Newer perspectives, grounded in string theory and the holographic principle, suggest that information may not be lost after all. One compelling idea proposes that it is encoded along the event horizon, like a cosmic hologram, preserving its details without allowing them to fall into the abyss. Another revolutionary concept involves Hawking radiation, in which radiation emitted by black holes might slowly release the trapped information, though in a heavily scrambled form. This ongoing clash between the laws of the very large and the very small continues to ignite debate and drive scientific progress. The rise of supermassive black holes. At the core of most galaxies lie enormous black holes, their masses ranging from millions to billions of times that of our Sun. These supermassive black holes are cosmic titans whose origins remain one of astronomy's most pressing mysteries. A leading theory suggests they began as intermediate mass black holes, slowly growing through the relentless consumption of gas, dust, and even entire stars. Through accretion and mergers with other black holes, they ballooned over time into the giants we observe today, like gravitational engines devouring all that comes near. Another hypothesis proposes that these colossal objects emerged early in the universe's history, just a few 100 million years after the Big Bang. In that young, dense cosmos, vast clouds of gas could have bypassed the star formation phase entirely, collapsing directly into black holes. This direct collapse model may help explain how such massive entities came to be so soon after the universe's birth. Galactic collisions also play a critical role. When two galaxies merge, their central black holes spiral together and eventually combine, forming an even larger one. These cataclysmic events funnel fresh material into the core, feeding the black hole and accelerating its growth. Over billions of years, these gravitational behemoths not only shape their host galaxies but also influence star formation and galactic structure. Unlocking their secrets gives us vital clues about the universe's own evolution. Hawking radiation. A window into the quantum abyss. In the 1970s, Stephen Hawking introduced a concept that revolutionized our view of black holes. They might not be eternal. According to quantum theory, even the vacuum of space is alive with fleeting virtual particles, pairs of particles and antiparticles that continuously appear and annihilate. Near a black hole's event horizon, these pairs can form such that one particle falls and while the other escapes. The escaping particle, observed as Hawking radiation, carries energy away from the black hole, gradually reducing its mass. This slow process, known as black hole evaporation, implies that black holes could eventually shrink and disappear. For most black holes, especially supermassive ones, this evaporation would unfold over incomprehensible spans of time, far longer than the age of the universe. But for smaller black holes, the process could accelerate as they shrink, ending in a dramatic final burst of energy before vanishing completely. Hawking radiation not only offers a mechanism for black hole death, but also forms a crucial bridge between quantum mechanics and general relativity. It serves as a rare intersection of the physics of the infinitesimal and the cosmic, hinting at a deeper unity in the laws that govern all matter and energy. Tapping the energy of rotating black holes. The idea of extracting energy from a black hole may sound like science fiction, but theoretical physics offers surprising possibilities. Rotating black holes, called Kerr black holes, possess enormous stores of rotational energy and angular momentum. In 1969, physicist Roger Penrose proposed a mechanism for accessing this power: the Penrose process. It centers on the ergosphere, a swirling region just outside the event horizon where spacetime itself is dragged along by the black hole's spin. In theory, if a particle enters the ergosphere and splits, one fragment can fall into the black hole while the other escapes, gaining more energy than the original particle had. This surplus energy would come from the black hole's rotation itself. While this remains a theoretical concept for now, it opens up thrilling possibilities not only for understanding extreme physics but perhaps, in some distant future, for harnessing the energy of the cosmos itself. Tapping into cosmic power, energy extraction from black holes. Within the swirling chaos of a rotating black hole lies a theoretical opportunity to extract energy, one that defies intuition yet is grounded in real physics. Inside the ergosphere, a distorted region of space-time just outside the event horizon, it is possible, at least on paper, to split a particle in two. One half plunges into the black hole while the other escapes, carrying away more energy than the original particle possessed. This clever maneuver, known as the Penrose process, effectively siphons a portion of the black hole's immense rotational energy. Another captivating mechanism is the Blandford-Znajek process, which theorizes that powerful magnetic fields near a spinning black hole can interact with its rotation to channel energy outward as electromagnetic radiation. These processes could help explain the high-speed particle jets we observe shooting from the centers of active galaxies, often stretching for thousands of light-years, possibly the visible aftermath of black hole-driven energy extraction. While these theories are elegant and provocative, transforming them into reality remains a monumental engineering challenge. The conditions required, extreme gravity, staggering energy levels, and magnetic environments beyond anything we can recreate, make direct energy extraction from black holes an unattainable goal for now. Still, contemplating these ideas deepens our understanding of relativistic physics and cosmic dynamics, pushing the boundaries of what might one day be technologically feasible. Falling into a black hole, a one-way voyage. What would it feel like to fall into a black hole? The answer depends largely on the black hole's mass. If you were to plunge into a stellar mass black hole only a few times the mass of our sun, your journey would be violently brief. As you approach the event horizon, tidal forces would rapidly increase. These intense gravitational differences across your body would stretch you vertically while compressing you horizontally, a gruesome process scientists have dubbed spaghettification. You would be torn apart well before crossing the event horizon. Surprisingly, falling into a supermassive black hole, millions or even billions of times more massive than the sun, might offer a less immediate death. The event horizon lies farther from the singularity, meaning the tidal forces at the boundary are weaker. In this case, you might pass the event horizon without noticing anything dramatic, at least initially. As you fall deeper, your view of the outside universe would distort into a brilliant point of light above you, slowly fading. Near the singularity, the very fabric of reality begins to unravel. Time and space lose their usual meaning, governed by unknown laws. You might encounter the singularity itself, where matter collapses to infinite density, or possibly pass through a wormhole, a hypothetical shortcut through space-time. Either way, the journey would mark a one-way descent into realms we cannot yet understand, guided only by mathematical speculation and the limits of imagination. Hunting worlds beyond. How we detect exoplanets. Discovering planets orbiting stars outside our solar system. Exoplanets requires innovation and precision. One of the most prolific techniques is the transit method. When a planet passes in front of its host star from our point of view, it blocks a tiny fraction of starlight. These subtle, periodic dips in brightness reveal the planet's size, orbit, and sometimes even clues about its atmosphere. Another powerful approach is the radial velocity method, also called the Doppler technique. As a planet orbits, its gravitational pull causes its star to wobble slightly. This movement shifts the star's light spectrum toward blue as it moves toward us and red as it moves away. Tracking these shifts allows scientists to estimate the planet's mass and orbital pattern. More challenging but visually rewarding is direct imaging. By using tools like coronagraphs or star shades to block out the star's overwhelming light, astronomers can photograph the faint glow of distant planets. Though still rare, this method helps characterize large exoplanets far from their stars. Another ingenious method is gravitational microlensing. When a massive object passes in front of a distant star, its gravity bends the background starlight. If a planet is part of the foreground system, it creates a specific signature in the light curve, acting like a natural magnifying glass. These techniques, often used in tandem, have led to the discovery of thousands of exoplanets, painting a portrait of planetary diversity far richer than we imagined. With every detection, we inch closer to understanding the vast architecture of our galaxy and perhaps finding life beyond Earth. The super-Earth puzzle, alien worlds between Earth and Neptune. Among the most intriguing classes of exoplanets are super-Earths, planets with masses between 1 and 10 times that of Earth. Though our own solar system lacks any planets in this mass range, these worlds are surprisingly common in the galaxy. They come in many forms: rocky planets with thin atmospheres, water-covered orbs with deep oceans, and everything in between. What makes super-Earths so compelling is their potential for habitability. Many orbit within their star's habitable zones, the region where temperatures could allow for liquid water. Given that water is essential for life as we know it, super-Earths become prime candidates in the search for alien biospheres. Spectroscopic observations during planetary transits can reveal the composition of their atmospheres, including the presence of gases like hydrogen, helium, or potentially even carbon-based compounds. This data offers clues about volcanic activity, climate, and the planet's internal structure. Beyond the quest for life, studying super-Earths helps solve puzzles in planetary formation theory. Why doesn't our solar system have such planets? Are they transitional stages between rocky and gas giants? Or are they common endpoints in other planetary systems? Every new super-Earth provides a piece of the cosmic puzzle, bringing us closer to understanding why planets form the way they do. Rogue planets, drifters in the dark floating freely through the galaxy without a parent star. Rogue planets are solitary wanderers shrouded in mystery. How they form and whether they can harbor life are questions that fascinate scientists. Deprived of starlight, these worlds face extreme conditions, but not necessarily lifeless ones. If a rogue planet retains internal heat from its formation or gains it through tidal interactions with a moon, it might host subsurface oceans beneath a thick layer of ice, much like Europa or Enceladus in our solar system. These hidden seas could provide a stable environment for microbial life, energized by underwater hydrothermal vents. Alternatively, a rogue planet with a dense atmosphere, rich in hydrogen or other insulating gases, might trap enough heat to maintain liquid water on or below its surface. This would allow a form of self-contained biosphere, independent of any star. Life on such planets, if it exists, might be based on chemical energy rather than sunlight. Earth's extremophiles, organisms that thrive in deep-sea vents or acidic lakes, show us that life can adapt to extreme and isolated conditions. Though the idea of life on rogue planets remains speculative, it pushes our thinking beyond traditional boundaries and challenges the notion that stars are a prerequisite for habitability. As our detection tools improve, we may one day glimpse these lonely nomads and discover whether life can truly thrive in the cosmic dark. Searching for biosignatures, signs of life from afar. One of the most exciting pursuits in modern science is the search for biosignatures, detectable signs of life on distant worlds. Using advanced instruments aboard telescopes, scientists analyze light passing through exoplanetary atmospheres, especially during transits, to search for chemical fingerprints that life may leave behind. Tracing the breath of life, biosignatures on distant worlds. When a planet passes in front of its host star, a sliver of starlight filters through its atmosphere. This light carries a hidden message, one that spectrometers can decode. By analyzing specific absorption lines, scientists identify the gases present in that alien atmosphere. Some, like oxygen, methane, or ozone, when found in particular ratios, may hint at biological processes. On Earth, for example, the simultaneous presence of oxygen and methane is largely attributed to life. Another powerful technique is direct imaging, where astronomers use specialized instruments to block out the overwhelming glare of a parent star and study the reflected light from the planet itself. This reflection carries signatures of surface materials and atmospheric compounds. The detection of chlorophyll-like features, for example, could point to processes akin to photosynthesis. Beyond biological signs, researchers are also searching for technosignatures, indicators of advanced technology. These could be structured light patterns, unusual infrared emissions, or radio signals not naturally occurring. Though speculative, the detection of such signals would be a historic revelation, offering the first evidence of intelligent life beyond Earth. Ambitious missions like Kepler and James Webb are already applying these methods, and future observatories will refine them further. Each advance sharpens our vision, bringing us closer to answering one of humanity's oldest questions. Are we alone in the universe? As we scan the skies, the search for biosignatures transforms from hopeful speculation into a grounded scientific pursuit, one that may soon reshape our understanding of life's reach in the cosmos. The Fermi Paradox. A cosmic silence. In 1950, physicist Enrico Fermi posed a simple yet haunting question. Where is everybody? Given the sheer number of stars and planets in the galaxy, intelligent life should be abundant. And yet, we have heard nothing. This conundrum is now known as the Fermi Paradox, and it lies at the intersection of statistical probability and observational silence. The Drake equation, a tool used to estimate the number of communicative civilizations, considers factors like star formation rates, the likelihood of Earth-like planets, and the development of intelligent life. According to its reasoning, our galaxy should be teeming with civilizations. Yet we observe no signs, no signals, no visits, no unmistakable artifacts. One possible explanation is the existence of a great filter, a stage in the development of life that is incredibly difficult to pass. This filter may lie behind us, suggesting that complex life is extremely rare. Or it may lie ahead, implying that technological civilizations tend to self-destruct before they can communicate across the stars. Some posit the zoo hypothesis that alien civilizations are aware of us but deliberately avoid contact, perhaps waiting for us to mature. Others propose that interstellar travel or communication is too energy-intensive or limited by physical constraints. Still more speculate that extraterrestrial life may be so different from us, biochemically or technologically, that we fail to recognize its presence. The Fermi paradox remains one of the most thought-provoking questions in modern science. Each proposed answer offers insights into our own fragility, potential futures, and the profound mystery of a universe that may be far more silent or stranger than we ever imagined. The Great Attractor, a cosmic tug-of-war deep in the cosmic expanse, lies an invisible force, one so powerful it draws entire clusters of galaxies toward it. Known as the Great Attractor, this gravitational anomaly lies some 150 to 250 million light-years away in the direction of the constellation Centaurus. It forms part of the Laniakea supercluster, a sprawling collection of over 100,000 galaxies, including our own. The mystery arises from the enormous gravitational pull this region exerts. Observations show that galaxies, including the Milky Way, are moving towards it at astonishing speeds, around 600 kilometers per second. Yet pinpointing its exact nature remains challenging due to its location in the zone of avoidance, where the view is blocked by the stars, gas, and dust of our own galaxy. Advanced X-ray astronomy and mapping techniques have revealed some of its structure. The Norma cluster, a massive galaxy cluster, is thought to lie near the center of this gravitational anomaly. However, the full scope and composition of the Great Attractor remain unresolved. It likely comprises vast amounts of dark matter, hot gas, and densely packed galaxies. Unraveling the nature of the Great Attractor helps us understand the motion of galaxies and the gravitational architecture of the universe on colossal scales. It exemplifies the hidden forces shaping the cosmos and offers a glimpse into how mass and motion govern the dance of galaxies across the fabric of space. Hypernovae, the titans of stellar death. Hypernovae are among the most energetic events in the universe, stellar explosions that far exceed the power of typical supernovae. Triggered by the collapse of stars at least 30 times the mass of the Sun, these cosmic cataclysms unleash torrents of energy when the star's core implodes, often resulting in the birth of a black hole. One of the hallmarks of hypernovae is their association with long-duration gamma-ray bursts, blinding flashes of radiation believed to be caused by relativistic jets of particles streaming from the star's poles as it collapses. Producing such jets requires finely tuned conditions, including rapid stellar rotation and immense core mass. Hypernovae don't merely end stars, they seed the cosmos. These explosions forge heavy elements beyond iron, scattering them across space. While ordinary supernovae also contribute to cosmic enrichment, hypernovae do so on a much grander scale, enriching future generations of stars and planets and leaving an indelible mark on the chemical evolution of the universe. Magnetars, beacons of magnetic fury. When massive stars die, they may leave behind neutron stars, compact remnants of collapsed cores. But under rare, extreme conditions, a special kind of neutron star forms, a magnetar, the universe's most magnetic object. Born from the explosive deaths of stars 10 to 25 times the mass of the Sun, magnetars arise when a collapsing stellar core spins rapidly and its magnetic fields are intensely compressed. The result, magnetic fields a quadrillion times stronger than Earth's. Inside the magnetar, particles, mostly neutrons, align their magnetic moments in unison, amplifying the overall magnetic effect. These tightly packed, ultradense structures create fields so unstable they can rupture the star's surface, unleashing starquakes and bursts of gamma rays that can be detected across galaxies, even influencing Earth's atmosphere. Magnetars are violent, unpredictable, and rare, but they offer unique windows into physics under conditions that cannot be replicated on Earth. Fast radio bursts. Millisecond mysteries. In 2007, astronomers detected a fleeting radio signal from beyond the Milky Way. Lasting just milliseconds, it carried as much energy as our sun emits in days. These events, now known as fast radio bursts, FRBs, remain one of astronomy's most baffling puzzles. One compelling theory suggests FRBs originate from magnetars undergoing magnetic upheaval or starquakes. Their intense magnetic fields can suddenly snap, releasing massive energy bursts detectable across the universe. Some FRBs are tied to regions where massive stars end their lives, reinforcing the magnetar hypothesis. Other theories point to collisions between compact objects, neutron stars, or black holes as possible sources. These violent mergers would release singular bursts, explaining one-off FRBs. Intriguingly, some FRBs repeat, hinting at ongoing activity rather than singular events. This opens the door to other possibilities. Perhaps binary systems or magnetar environment interactions are at play. With each newly observed burst, scientists inch closer to understanding these enigmatic flashes, brief but brilliant reminders of the dynamic nature of deep space. Binary stars, stellar partnerships, and cataclysmic consequences. Many stars are not alone. In binary systems, two stars orbit a common center of mass, and their interactions shape their life cycles in extraordinary ways. Early on, binary stars mainly interact through gravity. But as they age, the more massive star often evolves faster, swelling into a red giant. If it overflows its Roche lobe, the region where its gravity dominates, material can spill onto its companion. This mass transfer can accelerate the evolution of both stars. The receiving star may spin faster or ignite new fusion reactions. In some cases, if a white dwarf accretes too much material, it may explode in a type I supernova. Tightly bound binaries may eventually merge, forming massive stars or compact remnants like neutron stars. These systems can become X-ray binaries, where one star, now a black hole or neutron star, devours matter from its partner, emitting intense X-rays. Others evolve into millisecond pulsars, neutron stars spun up by the accreted material to dizzying speeds. Binary evolution reveals nature's creativity, showing that two stars together can lead to some of the most exotic phenomena in the cosmos. Quark stars, the next frontier of stellar collapse beyond neutron stars, may lie an even stranger possibility. Quark stars, objects composed of matter compressed so densely that neutrons themselves dissolve into their fundamental components, quarks. Under extreme pressure, a massive neutron star's core might exceed the critical threshold for stability. When this happens, neutrons may disintegrate into up, down, and possibly strange quarks, forming what's known as strange matter. A quark star would be incredibly small and dense. Matter falling onto it would be absorbed into the quark soup almost instantly, barely altering its size. Though difficult to distinguish from neutron stars, quark stars might have slightly different mass-radius relationships and cooling behaviors, providing observational clues. Though still theoretical, the existence of quark stars would offer unprecedented insight into quantum chromodynamics, the fundamental force binding quarks. If confirmed, they would redefine our understanding of matter under extreme conditions. Primordial black holes, dark matter's ancient shadow? Among the more speculative yet captivating hypotheses about dark matter is the idea that it could be composed of primordial black holes, exotic objects formed in the chaotic aftermath of the Big Bang. Unlike black holes that result from stellar collapse, these would have emerged from density fluctuations in the infant universe, possibly ranging in mass from subatomic scales to thousands of solar masses. Yet, the theory faces significant constraints. Primordial black holes of certain masses should emit detectable Hawking radiation or leave observational signatures through their gravitational interactions with stars and interstellar gas, but such effects remain unobserved. Additionally, data from the cosmic microwave background places strict limits on their possible contribution to the universe's total dark matter content. Still, interest in the idea has seen a resurgence. Observations from LIGO and Virgo, which detect gravitational waves from black hole mergers, have revealed events involving black holes of masses that could align with primordial origins. Ongoing research aims to explore unexplored mass ranges and refine detection methods. Should primordial black holes exist in meaningful quantities, their discovery could transform our understanding of dark matter and the early universe's formation. WIMPs, the leading particle dark matter candidate's a central contender in the search for dark matter is the weakly interacting massive particle, or WIMP. Predicted by theories that extend beyond the standard model of particle physics, such as supersymmetry, WIMPs are hypothesized to possess significant mass while interacting only through gravity and the weak nuclear force. These traits make them invisible to traditional detection, yet perfect candidates for explaining dark matter's gravitational effects. The so-called WIMP miracle lends weight to the theory. Calculations show that WIMPs created during the Big Bang would naturally yield a relic abundance closely matching current dark matter estimates, an elegant coincidence that has fueled decades of experimental pursuit. Detecting the undetectable, methods to find WIMPs and dark matter. To detect WIMPs directly, scientists employ ultra-sensitive underground detectors shielded from cosmic rays. Instruments filled with liquid xenon or argon, cooled to near absolute zero, await the rare moment when a WIMP might collide with an atomic nucleus, producing a tiny flash of light or a thermal signal. Experiments such as Xenonenti, LUX Zeppelin, and PandaX are leading this effort, pushing detection limits ever deeper. Indirect detection focuses on spotting the byproducts of WIMP annihilation, gamma rays, neutrinos, or positron-electron pairs that might result when two WIMPs collide. Space-based observatories like the Fermi Gamma Ray Space Telescope scan high-density regions such as the galactic center, seeking anomalous signals. Ground-based telescopes and neutrino detectors complement this search. A third frontier lies in particle accelerators like the Large Hadron Collider, where collisions recreate early universe conditions. If WIMPs are produced in these high-energy events, they might manifest as missing energy and momentum, indirect signs of particles that slip through detectors without interacting. Though WIMPs remain elusive, the pursuit continues to drive technological innovation and theoretical development, promising answers not only about dark matter but the fundamental architecture of matter itself. Ultra-high-energy cosmic rays, the universe's most energetic travelers scattered across the cosmos, are particles moving at speeds near light, packing energies millions of times greater than anything produced in earthbound accelerators. These are ultra-high-energy cosmic rays, UHICers, mostly protons or heavier atomic nuclei that defy easy explanation. One leading candidate for their origin is the active galactic nucleus, AGN, a supermassive black hole at the heart of a distant galaxy surrounded by a dense accretion disk and often launching relativistic jets. These jets may accelerate particles to astonishing speeds, flinging them across intergalactic space. Another source could be gamma-ray bursts, GRBs, brief but intensely energetic flashes resulting from massive stellar collapses or neutron star mergers. Their colossal explosions may generate the necessary shockwaves to produce UHICers. Supernova remnants, long known to generate lower-energy cosmic rays, could also contribute under specific conditions using Fermi acceleration mechanisms to boost particle speeds. As these particles travel through intergalactic space, magnetic fields twist and scatter their paths, further amplifying their energy via diffusive shock acceleration. To study them, scientists use vast ground-based observatories like the Pierre Auger Observatory in Argentina and the Telescope Array Project in Utah. These facilities detect secondary particles produced when UHICers strike Earth's atmosphere, helping to trace their elusive sources. While their origins remain uncertain, UHICers serve as natural probes of the most extreme processes in the universe and hold the potential to unlock new physics far beyond the reach of our laboratories. Decoding the sky, cosmic ray air showers, and the oh my god particle. When ultra-high-energy cosmic rays collide with Earth's atmosphere, they unleash particle cascades, gigantic showers of secondary particles. These events begin when a primary cosmic ray, typically a high-energy proton or heavy nucleus, slams into an atmospheric molecule at near-light speed. The resulting collision produces a storm of particles, pions, kaons, and other hadrons that rapidly decay into muons, electrons, neutrinos, and photons. This complex chain reaction spreads downward and outward, generating a shower front that can cover several square kilometers by the time it reaches the ground. Instruments like Cherenkov water tanks and scintillators detect the brief flashes of light and energetic signatures produced by these particles, allowing scientists to reconstruct the energy, trajectory, and composition of the original cosmic ray. One of the most astonishing cosmic rays ever recorded was the oh my god particle, detected on October 15, 1991. It carried an energy exceeding 300 million trillion electron volts, far surpassing anything ever generated in terrestrial particle accelerators. To grasp its magnitude, the energy in a single proton was comparable to a baseball traveling at 90 kilometers per hour. Its detection challenged existing astrophysical models. Even extreme sources like supernovae, gamma-ray bursts, and active galactic nuclei struggle to account for such high energies. Furthermore, the particle appeared to violate the GZK limit, a theoretical energy threshold above which cosmic rays should lose energy via interactions with the cosmic microwave background. Yet this proton seemed to arrive nearly intact. Since then, other ultra-energetic particles have been observed, but the original event remains iconic. These detections not only deepen the mystery of cosmic acceleration mechanisms, but also push the frontiers of astroparticle physics, hinting at phenomena we have yet to fully comprehend. Cosmic rays and human spaceflight, a hazard from the stars as humanity ventures beyond the protective layers of Earth's atmosphere and magnetic field. Cosmic rays become a serious challenge for space travel. These high-energy particles, originating from the Sun and distant astrophysical sources, pose both biological and technological risks. For astronauts, prolonged exposure to cosmic rays can damage DNA, disrupt cellular function, and elevate the risk of cancer, cataracts, and neurological disorders. Missions to the Moon, Mars, or deep space will significantly increase cumulative radiation exposure, necessitating robust protective measures. Cosmic rays also threaten spacecraft electronics. When a high-energy particle strikes a sensitive component, it can induce a single-event effect, potentially flipping bits, corrupting data, or damaging systems. Shielding is crucial, but mass constraints limit the use of heavy materials. Engineers use substances like polyethylene and even water for shielding, which offer partial protection. Mission planners also monitor solar activity, avoiding periods of heightened radiation when possible. Meanwhile, medical research is exploring pharmaceutical countermeasures to mitigate radiation's biological effects. Continuous monitoring through onboard radiation sensors helps assess exposure in real time, providing vital information for both crew safety and mission design. Addressing cosmic radiation is essential not only for survival in space, but for enabling long-duration exploration of the solar system. Neutrino detectors, windows into the invisible universe. Neutrinos are among the most elusive particles in nature. Nearly massless, chargeless, and barely interactive, they pass through ordinary matter like ghosts. Yet they carry priceless information from the universe's most violent and mysterious places. Because neutrinos can travel unhindered from the cores of stars, supernovae, or even the Big Bang, they serve as direct messengers from otherwise inaccessible realms. Unlike light or cosmic rays, neutrinos aren't deflected by magnetic fields or absorbed by interstellar dust. Detecting them, however, is incredibly difficult. It requires massive volumes of material, ice, water, or liquid scintillators watched by arrays of photodetectors that wait for the rare moment when a neutrino interacts with an atomic nucleus, producing a tiny flash of light. Facilities like Super Cameo Candy in Japan and IceCube in Antarctica are among the world's foremost neutrino observatories. They've helped us peer into solar fusion, supernova explosions, and even blazar jets, enriching our understanding of both particle physics and astrophysics. In essence, neutrino detectors act as cosmic ears, picking up faint whispers from the neutrinos. Probes of the sun, supernovae, and fundamental physics. The sun, in its heart, sustains itself through nuclear fusion, reactions that also produce an enormous flux of neutrinos. These ghostly particles pass unimpeded from the core of our star to Earth, giving scientists a direct glimpse into solar processes that no light or heat can reveal. By studying solar neutrinos, researchers have confirmed key aspects of stellar structure and energy generation, grounding our models of star physics in observational reality. Similarly, neutrinos from supernovae provide an unfiltered view into the violent deaths of massive stars. These particles escape from the collapsing core before light does, carrying vital information about the formation of neutron stars, black holes, and the synthesis of heavy elements that seed the galaxy. Even more profoundly, the discovery that neutrinos can oscillate, changing from one type to another during flight, proved that they have mass, shattering long-held assumptions and forcing revisions to the standard model of particle physics. These oscillations open a window into physics beyond the known forces and particles. Now, as we detect neutrinos from extragalactic sources, possibly born in active galactic nuclei or gamma-ray bursts, we gain access to realms of high-energy astrophysics otherwise beyond reach. Neutrinos thus serve as silent messengers from both the deep interior of stars and the farthest corners of the universe, offering unparalleled insights into the fundamental workings of the cosmos. Time dilation and GPS, relativity in everyday life. Among the most compelling confirmations of Einstein's relativity lies in an everyday convenience, the Global Positioning System, GPS. This satellite-based navigation system relies on precise time synchronization between satellites orbiting the Earth and receivers on the ground. But due to their altitude and velocity, satellites experience time differently. According to general relativity, clocks in weaker gravitational fields, farther from Earth's mass, tick slightly faster. Meanwhile, special relativity predicts that moving clocks tick more slowly. These effects don't cancel, they compound, causing satellite clocks to run about 38 microseconds faster per day than those on Earth. Without correcting for this discrepancy, GPS position errors would accumulate by 10 kilometers per day. To prevent this, satellite clocks are pre-adjusted before launch, and onboard systems continuously compensate for time dilation effects. This elegant application of theoretical physics ensures precise functioning for everything from smartphone maps to telecommunications, financial systems, and emergency services. It is a striking reminder that our understanding of space-time is not merely abstract, but embedded in the fabric of modern civilization. Gravitational waves. Echoes of the universe's most violent events, first predicted by Einstein in 1916, Gravitational waves are ripples in the very fabric of space-time, generated by cataclysmic cosmic events, colliding black holes, neutron star mergers, and supernovae. These waves propagate across the cosmos at light speed, carrying information about the motion and mass of their sources. Detecting them requires astonishing precision. LIGO, the Laser Interferometer Gravitational Wave Observatory, achieves this by splitting laser beams along two perpendicular arms, each kilometers long. If a gravitational wave passes through, it alters the lengths of the arms by less than the width of a proton, creating a measurable interference pattern. In 2015, LIGO made history by capturing gravitational waves from a binary black hole merger, confirming a century-old prediction and inaugurating the age of gravitational wave astronomy. Since then, collaborations with other detectors like Virgo and CAGRA have refined our ability to locate sources and analyze waveforms. Gravitational waves reveal cosmic events invisible to traditional telescopes, allowing scientists to peer into environments of extreme gravity and energy. They are transforming our understanding of how mass, energy, and space-time behave at the most fundamental level. Wormholes, theoretical gateways through space-time. Among the most tantalizing concepts in modern physics is the wormhole, a theoretical bridge connecting two distant points in space-time. Derived from certain solutions to Einstein's equations, wormholes evoke the possibility of faster-than-light travel and even time manipulation. Imagine space-time as a fabric. A wormhole bends this fabric, creating a shortcut, a tunnel, between far-separated regions of the universe. In principle, passing through it would allow instantaneous travel over vast cosmic distances. However, theory presents daunting obstacles. Stability is the foremost challenge. Most wormhole solutions collapse too quickly for anything to pass through. To keep a wormhole open, one would need exotic matter, a substance with negative energy density capable of repelling gravitational collapse. This kind of matter remains hypothetical, and we currently lack the technology or understanding to create or sustain it. Still, wormholes remain a fertile ground for speculation and research, linking ideas in quantum gravity, string theory, and cosmology. Though purely theoretical for now, the exploration of wormholes reflects our deepest curiosity, not just about where we are in the universe, but how we might one day move through it in unimaginable ways. Wormholes and the boundaries of physics. Even if we could somehow stabilize a wormhole, questions remain about its safety and practical traversability. Near the wormhole's throat, the narrowest region, gravitational forces could become so intense that they would stretch and compress any matter attempting to pass through, a process ominously known as spaghettification. Additionally, many wormhole models raise theoretical red flags. Some solutions in general relativity imply the potential for causality violations, including time travel. Such paradoxes, like returning to a point in time before one departed, challenge our most basic assumptions about cause and effect. To date, no empirical evidence supports the existence of wormholes, and their construction or use remains far beyond our current scientific reach. Nevertheless, they serve as powerful thought experiments, pushing the limits of space-time geometry, quantum theory, and our conceptual understanding of the universe. Though not yet practical, wormholes continue to provoke bold questions about the true nature of reality. Frame dragging, twisting the fabric of space-time. Frame dragging, also known as the lens-stirring effect, is a remarkable prediction of general relativity. When a massive object spins, it doesn't just warp space-time, it twists it. Imagine space-time as a thick fluid and a rotating body, like a neutron star or black hole, as a spoon stirring that fluid. The rotation causes nearby space-time to spiral, dragging inertial frames along with it. This effect grows stronger the closer one gets to the rotating mass and is especially intense near rapidly spinning black holes. Detecting frame dragging on Earth is difficult, but not impossible. NASA's Gravity Probe B, launched in 2004, carried gyroscopes so precise they could detect tiny angular shifts caused by Earth's rotation dragging spacetime. After extensive analysis, the mission confirmed the phenomenon, one of the most delicate experimental validations of general relativity to date. Frame dragging has profound implications in astrophysical contexts. Near rotating black holes, it can dictate the motion of matter in accretion disks, shape relativistic jets, and influence the orbits of particles and even light itself. By measuring and modeling this effect, scientists gain valuable insight into some of the most extreme environments in the universe. The twin paradox, time travel without a machine. One of the most famous illustrations of time dilation comes from the twin paradox, a thought experiment derived from special relativity. Imagine two identical twins. One remains on Earth while the other boards a spacecraft traveling near the speed of light. According to special relativity, time aboard the fast-moving spacecraft passes more slowly than it does on Earth. If the traveling twin embarks on a journey to a distant star and then returns, they will have aged less than their sibling who stayed behind. For example, while the Earthbound twin may have experienced 10 years, the traveling twin might feel as though only a few years have passed. This result arises not from malfunctioning clocks or biological effects, but from the fundamental structure of spacetime itself. Moving clocks tick slower relative to stationary observers. Though it seems paradoxical, it is a confirmed consequence of Einstein's equations, validated by experiments with fast-moving particles, atomic clocks on jets, and satellites in orbit. The twin paradox captures a profound truth. Time is not absolute, but relative, dependent on speed and gravity. What seems like science fiction becomes science fact, revealing just how strange and beautiful our universe truly is. The twin paradox. Symmetry broken by acceleration. A natural question arises when contemplating the twin paradox. If both twins perceive the other as moving, why don't they experience time dilation equally? The resolution lies in the asymmetry of their experiences. The twin aboard the spacecraft undergoes acceleration and deceleration, transitioning between different reference frames, whereas the Earthbound twin remains in a single inertial frame. This shift breaks the symmetry and ensures that the traveling twin ages less upon reunion. Though the paradox may seem abstract, its implications are tangible. The same relativistic principles apply to GPS satellites, where time dilation must be corrected to maintain accuracy. The twin paradox thus offers a profound and practical lesson in how motion, gravity, and time are intertwined, revealing a universe far stranger than everyday intuition might suggest. The gamma-ray glow at the galactic center at the heart of the Milky Way lies a persistent mystery, a diffuse, high-energy gamma-ray emission known as the galactic center GeV excess. Detected by instruments such as the Fermi Gamma-Ray Space Telescope, this glow radiates from the densely packed and energetically active regions surrounding the supermassive black hole Sagittarius A star. One tantalizing explanation posits that this glow is the result of dark matter annihilation. If dark matter consists of particles capable of colliding and annihilating, the dense galactic core would be an ideal environment for such interactions. The resulting gamma rays would provide indirect evidence for the nature of this mysterious substance. Another compelling theory points to millisecond pulsars, rapidly spinning neutron stars that emit beams of radiation, including gamma rays. Their abundance in the inner galactic regions could collectively account for the observed glow. If confirmed, it would reshape our understanding of the stellar population and evolutionary history of the galactic center. Alternatively, the excess could be caused by cosmic rays colliding with dense gas clouds in the region. These interactions would produce gamma rays through known particle physics mechanisms, amplified by the intense magnetic fields and turbulent dynamics near the galaxy's core. Each hypothesis, whether involving dark matter or conventional astrophysical sources, offers a unique window into high-energy processes in one of the most enigmatic regions of our galaxy. Solving this mystery could lead to transformative insights into the structure of the cosmos and the particles that govern it. Supermassive stars. Cosmic beacons of extremes. Among the most extraordinary stellar objects are supermassive stars like our 136A1, located in the R136 cluster within the Large Magellanic Cloud. Weighing in at over 200 times the mass of the Sun, these stellar giants challenge our understanding of how stars form and evolve. Their birth begins within giant molecular clouds, cold, dense regions of interstellar gas and dust. For a star to reach such an enormous mass, the progenitor cloud must undergo rapid and sustained gravitational collapse, gathering massive amounts of material in a short time frame. In star-forming regions like our 136, external influences, including the radiation pressure and gravitational pull from neighboring stars, can actually enhance accretion by clearing surrounding gas, allowing the protostar to feed more efficiently. Yet, as the star grows, its own intense radiation pressure pushes back against further accumulation. Balancing this force with gravitational infall requires finely tuned conditions, and the star may only continue growing if accretion outpaces radiation-driven dispersion. The existence of stars like our 136A1 forces astronomers to reconsider traditional models of stellar growth, stability, and longevity. These cosmic titans not only blaze with incredible luminosity but may also end their lives as hypernovae or black holes, profoundly influencing their galactic environments. Galaxies are not isolated islands in space. They interact, merge, and reshape one another under the influence of gravity. When two galaxies begin to draw closer due to mutual gravitational attraction, the event that unfolds is not a chaotic crash of stars but a majestic, slow-motion ballet stretching across millions or even billions of years. Despite their size, the vast distances between individual stars mean that direct stellar collisions are exceedingly rare. Instead, it's the gravitational interplay among stars, gas clouds, and dark matter that drives the transformation. As galaxies near each other, they experience intense tidal forces that distort their spiral arms, twist their structures, and fling long streams of gas and stars into intergalactic space. These distortions often trigger waves of star formation as gas clouds become compressed. These intense stellar birth events, called starbursts, can lead to the rapid creation of new stars far exceeding normal rates. Though galaxies may pass through each other initially, gravitational attraction pulls them back again and again until they eventually merge. Over time, chaotic motions settle into a more stable configuration and the original galaxies fuse into a single, larger one. When spiral galaxies merge, the result is often an elliptical galaxy with a spheroidal shape and stars moving in random orbits. These mergers are a cornerstone of the hierarchical model of cosmic evolution, which explains how small structures in the early universe gradually combined to form the large-scale structures we observe today. Observational evidence from numerous galaxies across the sky confirms that mergers have played a pivotal role in shaping the universe's history. Extracting resources from asteroids poses a host of challenges, both technical and regulatory. One major concern is how to handle and process the harvested material. Should it be refined on-site or transported to another destination like Earth or a space station? Designing systems that can autonomously manage such operations without constant human supervision remains a formidable task. The energy demands for extraction, processing, and transportation are immense, often requiring advanced power solutions such as high-efficiency solar panels or compact nuclear reactors. Yet the hurdles go beyond engineering. The legal landscape remains uncertain. The 1967 Outer Space Treaty, ratified by many nations, prohibits the appropriation of celestial bodies by any country. This creates ambiguity around the ownership of asteroid resources. As interest in space mining grows, the global community faces urgent questions. Who has the right to exploit these resources? How can fairness and sustainability be ensured? To move forward, international agreements and regulations must evolve to balance exploration with ethical responsibility. Fusion, the core engine of stellar energy, requires light atomic nuclei to merge into heavier ones, releasing immense energy in the process. However, these positively charged nuclei naturally repel one another due to the Coulomb barrier, a force of electrostatic repulsion that prevents them from coming close enough for the strong nuclear force to bind them. Classically, overcoming this barrier would demand temperatures and kinetic energy far beyond what we observe, even in the heart of stars. Fortunately, quantum mechanics introduces a phenomenon known as quantum tunneling, which allows particles to pass through energy barriers they lack the classical energy to overcome. Because quantum particles behave as probability waves, there's a non-zero chance of finding them on the other side of the barrier, even when classical mechanics deems it impossible. In the dense, searing core of a star, this quantum leeway becomes crucial. The sheer number of protons interacting ensures that tunneling probabilities accumulate, allowing fusion to occur with surprising regularity. Without this quantum shortcut, stars would require unattainably high temperatures to initiate fusion, making the stable burning of hydrogen, and, by extension, the energy source of stars untenable. Quantum tunneling, then, is not just a mathematical curiosity, but the very reason stars like our sun shine and sustain life-bearing worlds like Earth. Whole black holes and the quantum realm. Quantum physics also revolutionizes our understanding of black holes, especially near their event horizons. One of the most groundbreaking ideas in this domain is Hawking radiation, proposed by Stephen Hawking. Contrary to their image as completely dark voids, black holes may emit faint radiation due to quantum effects. Near the event horizon, the quantum vacuum buzzes with virtual particle-antiparticle pairs. Normally, these pairs annihilate quickly, but a powerful gravitational field can pull them apart. If one particle is captured by the black hole and the other escapes, the escaping particle becomes Hawking radiation, carrying away energy and gradually reducing the black hole's mass. Though this radiation is negligible for large black holes, it may become significant for smaller ones, potentially leading to their evaporation over immense timescales. Black holes also confront physicists with the information paradox. Classical relativity suggests that anything falling into a black hole is lost forever, including its information, while quantum mechanics asserts that information can never be truly destroyed. Resolving this contradiction has led to bold ideas, such as the holographic principle, which posits that all information absorbed by a black hole could be encoded on its surface, preserving it in a radically different form. Moreover, efforts to bridge quantum theory and general relativity, such as string theory and loop quantum gravity, seek to describe what happens inside black holes, potentially avoiding singularities altogether. If successful, these theories could reveal that black holes are not points of infinite density but structures governed by a deeper quantum architecture. Milky Way quantum foam and the granular nature of spacetime at unimaginably small scales, around the Planck length, 10 to the power of -35 meters, spacetime may not be smooth as once believed but wildly chaotic. This concept, known as quantum foam or spacetime foam, was introduced by physicist John Wheeler. It envisions the universe's very fabric as a seething ocean of energy fluctuations, where virtual particles constantly appear and vanish due to the Heisenberg uncertainty principle. Rather than a tranquil void, space-time at these scales is a frothy, turbulent arena where geometry itself shifts moment to moment. These fluctuations might leave subtle imprints even at cosmic distances, potentially affecting the travel of photons or gravitational waves. Theoretical approaches like string theory and loop quantum gravity offer different frameworks to describe this foam, some suggesting that space-time may be discrete rather than continuous, or that hidden dimensions could emerge at such scales. Quantum foam is more than a theoretical curiosity. It may hold the key to unifying the fundamental forces and explaining the structure of space-time at its most fundamental level. Shooting star quantum fluctuations and the birth of the cosmos. The seeds of galaxies, stars, and cosmic structure may trace back to minute quantum fluctuations in the very earliest moments of the universe. Immediately following the Big Bang, the universe was dominated by extreme heat and density. At these scales, the principles of quantum mechanics prevailed. During this brief but explosive inflationary epoch, the universe expanded exponentially within a tiny fraction of a second. Tiny, random variations in energy density, born from quantum uncertainty, were stretched to astronomical proportions. These fluctuations became embedded into the fabric of spacetime itself. As the universe cooled and matter coalesced, regions with slightly higher density exerted more gravitational pull, attracting more matter and forming the cosmic web of galaxies and clusters we observe today. Meanwhile, areas with less density became cosmic voids, vast expanses of relative emptiness. What began as ephemeral quantum whispers in the vacuum of space ultimately shaped the large-scale structure of the universe. This profound transformation from the quantum to the cosmic offers one of the most awe-inspiring narratives in modern physics.